What if you could train short networks and run inference on large networks? By having this setup, you will get the training speed up and stability from shorter networks, while benefiting from the stronger performance of larger network when it's time to test. This is the idea explored by the Stochastic Depth training methodology. In this tutorial, we will look at the paper and check out the Pytorch implementation of the methodology for resnet. The paper is fairly straightforward and easy to read. I recommend it. Check it out, it's linked into the description. So let's start with exploring the background around which this research was conducted. So there are two main problems when training deep network. The first one is the vanishing gradient, or exploding in some instance problem. Since the networks are deep and there are a lot of multiplication involved when pushing information through the network, small gradients get smaller over time. Another more practical issue is that training deeper network is very time consuming, where most of the computation are being taken in a forward and backward pass. So the residual neural network architecture, with its simple residual skip connection idea, made it much simpler to train deep networks. It broke a huge barrier in training deeper networks, which were facing a degradation of their training performance at the time. With residual neural network, training deeper network was more than possible. Hundreds and even thousands of layers could now be trained with competitive results. The architecture that made it possible was quite simple. As a reminder, the core residual block has a shortcut connection which passes forward the input. The whole rationale is that if a shorter network is optimal, the layer layers don't have to learn anything. They can just pass along the output of the shorter network. By the way, if you are interested in doing a deep dive on the ResNet architecture, check out my video on the subject. However, even for residual neural network, training thousands of layers was difficult. The original paper pushed the network depth to 1,000 of layers and overfitted on Cypher 10. Dropout is a very pretty good regularization method with a simple mechanic. Dropout stochastically kills off a neuron throughout the training procedure, which has a nice effect of reducing codependency across neurons. Using dropout then is a bit similar to training an ensemble of network, since throughout the training procedure we have different neurons being used to generate the output. Ensemble of network, by the way, is usually the most performant type of architecture. In the ResNet paper, the ensemble of network had the overall best result. The author then decided to take these two ideas and combine them to create stochastic depth. They kept the simplicity of residual neural network architecture with the regularization idea of dropout. This is how they came up with this core idea of training on small network and testing on deep network. So this begs a question. How did they manage this training procedure of having small network without sacrificing performance? Similarly, another very important question is, why did they use residual neural network to start with? So let's find out by looking at the architecture. So let's start with actually the second question. Why use the ResNet architecture to do that? Why not another VGG network or like AlexNet? The solution to their train small and test large was to apply dropout on a full layer basis instead of individual neurons. As you can see in this image from the paper, each of the layer has a probability of survival, which ultimately dictate how often a whole layer shut down during a batch of training. The first layer has a probability of 100%, while the last layer has a varying probability. In the paper, it was 50%. This probability was controlling a Bernoulli random variable, which could take either a 1 or a 0 value. The author furthermore found out that using a linear decay of the survival probability was favorable instead of a uniform distribution. This means the first layer has the highest probability, then the last one, and the intermediate probability are following a decaying formula like in the screen. So let's see an example in action during training time. Here we have the residual block and the composite function h. If you see here, there's a Bernoulli random variable BL, which will be 0, 1 depending on the probability P. This will change the way the information is moving through the residual block. If B is equal to 1, this variable doesn't change anything to the original residual block, so we basically have the same thing. It will just act as in the ResNet paper. It's the same formula with the same structure. However, if B is equal to 0, a whole chunk of the formula will be like zeroed. So we will therefore have solely the identity part of the residual connection still working, whose sole purpose is to move the input to the output, effectively skipping the block layer entirely. At this time, the author proposed to multiply by the probability P the output of the function f. The choice is interesting, But as we'll see on the code later on, it might be more stable to just run it without multiplying IP. So this architecture change actually answered the following question: why use the resnet architecture for stochastic depth? The answer is that it's very easy to implement in code, therefore making it a logical choice. Now on to the first question. How do they manage this without sacrificing performance? The key to answer this question is to see how dropout and stochastic depth behave differently as a regularizer. In dropout, you obtain a thinner network as you target randomly the neurons. The network is still as large as before, it just has less width. With stochastic depth, what ends up happening is that a whole layer gets deleted from a specific training batch. This leads to shorter network. So the expected network depth is therefore given by this formula here, depending on the probability of survival that we need to sum up, which effectively means that it's as if we were training one network of size E of L over the course of the whole training with stochastic depth. This leads to significant speedup in the testing with different benchmarks. They were able to obtain like roughly 25% speedup using a linear decay to 50%. Speedup, we get that. Now, how about performance? Additionally, stochastic depth and dropout can be thought as acting as a kind of implicit model ensemble. It's as if by applying one of these regulation methods, we are training n number of networks and using their ensemble result during the testing phase. So in dropout case, we have an ensemble of 2 to the L network where L is the number of layers. Let's look at an example here with layer size of 2. Each of the hidden layer can either be on or off depending on their survival probability. Therefore, we have 2 to the 2 network, which in this case it's 4. So we should have 4 network at the end. Let's look at what each of these 4 networks look like. So the network 1 could be one everything is on, like a regular constant depth network. Network 2 can be the one where the first hidden layer is knocked out. Network 3 is when the last hidden layer is knocked out, and network 4 is when all hidden layers are knocked out and we're just passing the input to the output. Therefore, the full training ensemble will look something like this, with the 4 networks contributing to the final output of the training network. So as you can see here, each of these 4 networks have different depth. Therefore, for the question of how do they manage training small network and using large network during testing without sacrificing performance, because stochastic depth is similar to using ensemble techniques, which are usually the best for neural network, as we've seen in the ResNet paper. So the dataset used in this paper was the 3 usual suspects, so we're going to go through them quickly. We have Cypher 10 and 100, which are about 60k image, split in either 10 or 100 class. We have SVHN, which is 600,000 image of digit taken from Google Street View. And we have ImageNet, which you use here, like in the ResNet, to benchmark properly with existing state-of-the-art networks. Let's look at the main result now. First off, stochastic depth was better than constant depth for both Cypher and CVHN, although marginally for the last one. They even were able to gain a state-of-the-art at the time on the CIFAR benchmark. Checking CIFAR in more depth, we have the following. So Cypher 10, for 110 layer, we have a solid gap between the two during the test set. So the stochastic depth is much better. Same story is happening on Cypher 100. It seemed like on this dataset, the regularization effect of stochastic depth was beneficial. This is even apparent on the order of magnitude more layer with the 1,202 layer residual neural network. As we can see with the constant depth ResNet, we have an overfitting happening from 110 to 1,000 layers, while with stochastic depth, we do not have this issue. That's the regularization effect of stochastic depth in action. A similar story is shaping up with the 152 layer ResNet on SVHN. As we can see here, even it's a bit more unstable for the stochastic depth, we have 5% more performance than in constant depth. However, we do not get the same effect on the ImageNet dataset, which was interesting. As we see, the constant depth and the stochastic depth for the 152 layer network yield roughly the same result. The others were able to get better result by training for the same amount of time, but when they let the constant depth train for the same epoch length as stochastic depth, it was still underperforming. It's interesting to note here that for the ImageNet, they used the bottleneck block instead of the basic block for residual neural network. This might have had an impact. As a reminder, the bottleneck block used for residual neural network looked like this, with the one-on-one convolution at the start. This was used by the ResNet author Perley to speed up training when dealing with deeper network. Anyway, let's look at a few more results before jumping into the Pytorch code. First off, the stochastic depth has healthier mean gradient magnitude in general than constant depth, which means that the vanishing gradient issue has less of an effect in stochastic depth network than in constant depth network. Also, stochastic depth was shown to give more speed up and better performance across different survival probability, not just the 0.5 one. If we zoom into the left plot, we see that survival probability as a function of test error for tree methodology. Here we have linear decay for stochastic depth, uniform stochastic depth, so probability is the same everywhere, and just constant depth. In this instance where stochastic depth was more performant than constant depth, we even see a speed up of 1.3 to 2 times the constant depth. If we look to the right plot at the test error heat map for the probability of survival versus network depth, we see that a deeper network with smaller probability of survival have the best training error of the bunch. This highlights the effect of depth in network performance as well as the regularization effect of a strategy like stochastic depth. It also makes it very clear why they choose a linear decay with the last p being 0.5, since empirically it gives the best result. Okay, let's now jump into an actual Pytorch code to see more implementation detail. As a disclaimer, this is not the original code that the author gave. It was coded in Lua. I've actually found a code in Pytorch that is pretty legit. Let's dive into it. So most of the code that we're going to review today is coming from this. I've edited it, right, a bit so that it's a bit more understandable. But this is a good place to store it, fork it, check it out if you want to. There's also an implementation directly on Pytorch about the stochastic depth operator. Yeah, but this one is pretty good. The guy that made it is working at Facebook actually. Yep, Reality Lab. So pretty good one, check it out. Okay, so you can check it out here into my GitHub repository. I took the relevant portion of the code and put it there. It's under stochastic depth. There's a README over here that will show you like all of my thought process while like going through the code base. And in stochasticdepth.py, which is not a workable piece of code, I cut it down to only the thing you need in order to understand how it's structured and how it's implemented. So let's dive into it. We have the resnet 18 stochastic depth linear decay function here, which will be used like this. You call it like this, resnet blah blah blah, and then you give it like is it pre-trained or not, the probability is 0L, and the multi-flag variable here, and then you get it here. So just a disclaimer here, it doesn't follow the same structure as a Pytorch native implementation. So just a disclaimer. So the source code for this resnet 18 stochastic depth linear decay look like this, right? You have this variable pre-train, prob, multi-flag here, and then there's a bunch of things. And it's like in Pytorch documentation, this is just a wrapper function on the actual thing that is going to create the class and all of the stuff. The three things of interest, pre-train is defining if we load the model or not, right? So the pre-train weight. Here in this example, we're going to look at resnet 18. The prob 0L is, it's actually an array of two numbers. It's the starting probability and the last layer probability. This could have been like two numbers, actually a tuple or something, but yeah, the guy decided to make an array. Multi-flag here will be used somewhere in the code because, like I said in the presentation, during testing time, the author decided to do a multiplication with the probability with the output of the function. The guy that made this found out that it actually is better to just not do that, but he give you the parameter here to do it or not. So if it's multi-flagged to true, you're actually going to do it, this multiplication. If you set it to false, you're not going to do it. Then there's a bunch of other parameters that we're going to see in a few. So let's actually dive into ResNet here. But before we go there, we're going to actually go into the building block for this. So ResNet stochastic depth linear decay is the class that matters, but there's other classes that are going to get composed in this big class that we're going to see in a few. So first one is stochastic depth basic block. So basic block, remember, it's the building block of a resnet. And we have the following here. We have a constructor, we have a forward pass, and then that's it. So that's all that we have here. We're gonna deconstruct each of the stuff bit by bit. There's the constructor over here, and then like it's mostly normal stuff that is happening. The variable here that is important is self.m, which I don't know why they chose m. It could have been b for to match the paper, but whatever. This is the Bernoulli random variable, which either be going to be 0 or 1. And here, this is where we insert the probability that it's going to be 0 or 1. That's how it's set up. So this one is important. So take that in mind when we're going to look at the rest of the stuff. This will be used in the forward function. Let's look at it. It's a bit big, and it's like has kind of 3 main block here. So look like this. We have an identity here, if self.training here. We have an if statement here, else statement here, and then this is happening when we're not training. This is when we're testing. So let's deconstruct that bit by bit. So the first thing is the identity. So x.clone, we take that and we put it into this variable identity, exactly like in the ResNet paper. So this is this branch that we're taking. We're making a copy of it. That's this, and then the training loop, right? It's here. It's without the else that we found afterward. So there's 2 main blocks. There's if torch equals self.sample, and if this sample give us ones, then we're going to do that. If they give us 0, we're going to do the else, right? So this, remember this m over here is our Bernoulli random variable. So let's take a look at the first block. So here, this is actually where we're going to be deciding if like we're knocking out this layer or not. That's where this thing is happening. So if this is equal to 1, we're not. If it's equal to 0, we're just going to skip it. So what we're going to do here, if turn 0 is equal to 1, we're going to do our pass or output to the conv batch normalization, ReLU conv batch normalization thing, like that thing over here. And then if we have to downsample, we do it. But then we just run our normal basic block as in the ResNet architecture, basic stuff. And then we add our identity to the output. If it's 0 though, what we do is none of this. Like we just don't do that. You see here, require grads true. So then in the back propagation, we're gonna do something about it. If require grads false here, because we shut it off, we're not gonna do any of that. We're still gonna do the downsample if we need to for the identity thing, but that's kind of it. And then the output will gonna be equal to the identity before the final value. So we're just not pushing our stuff through these layers. So if we look at the testing loop, which is the out of the first if statement, so in this else, what is actually different is we're still doing like conv batch normalization ReLU, conv batch normalization, downsample if we need to, but then here, if we set the multi-flag to true, we actually gonna do the probability times out this thing plus the identity. So this is the formula that we saw in the paper, this one here with the P. What the author of this code is saying is that maybe you shouldn't do that, and you should just do out plus identity, and you don't have to scale the output with the probability of this layer. It was not really explained in the paper why they were doing this, and if there's like difference when they were not. So you just test it out yourself, which one worked best for you. So that's this for the building block, right? So stochastic, that basic block. Let's take a look at how this is used inside the actual ResNet architecture. So we have this ResNet stochastic depth linear decay, that thing that we saw at the start. And it's fairly big, but it has the same exact structure as the ResNet architecture in Pytorch. So if you're a bit confused here and I'm going too fast, take a look at this video, because I'm deconstructing in this video also the ResNet architecture. So we have a constructor here, right? Some initialization that we're doing here. We have the make layer function, like in ResNet. We have the forward function, and then that's that. That's kind of it. So there's these 3 blocks. So let's actually go backward. We're going to look at the forward block, then we're going to look at the make layer, and then we're going to finish by the constructor. So the forward block is pretty simple. It's exactly this figure in the original ResNet paper. So here we have at first we have the first input kind of block that is same for everybody, every type of resnet architecture we're doing. So 18, 34, 50, 101, 150. We're doing this thing, like 7 by 7, blah, blah, 3 by 3, max pooling. This is what's happening over here. Then for every network, it's the same thing. We have these 4 big layers. So this one, this one, this one, and this one. So these 4 big layers have layers inside of them, right? So you can see there's multiple layers in each of them, and there's block repeating. Here, these are the bottleneck block. This is the basic block. So in our case, we're in this case over here. And basically we're running through the layer that we created as a module. And then at the end, we're always doing this. So this part that is the same for every type of network. That's it. Nothing too specific, right? For the stochastic depth, it's more as a resnet kind of implementation. The stochastic depth, we're gonna see it happening into the make layers. Okay, so now we have the make layer function. So this function, it takes a block, the block type that we want to run. And then we're going to go through the motion of creating each of these block into that layer and just appending it to the layer. So you see here we have layers, an array, and then we're doing a bunch of appending, and then we're doing a bunch of manipulation on the probability. And at the end, we're iterating on the layers, and we're just adding layers and layers and layers. There's a few difference between the motion we're doing here and the motion we're doing here. This one is out of this loop because we're maybe doing downsample because of the output of the previous layer. So this is something that is going on. We don't need this variable when we're going here because we're not doing any downsampling. Yeah, so that's that. Let's take a look at like these highlighted part, right? Those are the most important one for our understanding of stochastic depth. So here we have layers.append, and then we have block, and this block is defined whenever we're going to call make layer. So we're going to see it in the constructor. Then there's the current probability. We define if we do the mult flag or not. There's this input stuff, and then the downsampling thing. That's it. Here, this prob now equal prob now minus prob step. Prob step is the decrement that we need to do as we're going through the linear decay. It's based on this rule over here. We're going to see it in the constructor. And then we repeat the process multiple times without downsampling. We're just appending, and then we're creating a block, jamming it into there, and then we're decrementing the probability. So as we go, there's going to be a linear decay happening. Let's take a look at the last thing, the init function. So here we have, it's fairly big. It's actually broken down to 3 parts. There's this part, right, which is like just the setup of the different variables that we're going to need in the forward function. Then there's the initialization over here that is important. So let's take a look at all of them. So the first block of parameterization is very, very simple. We just define what we need here depending on like the table in the resnet specification. And then here, this is where we're defining the different probability. We're calculating the delta here, the step that we need based on the number of layers that we have. It's exactly the formula over there. And that's that. This is like pretty simple constructor stuff. And then we have the layer construction step just here, where we're doing self.makeLayer, we call the function, with the block type that we want. And then we give the proper parameter for this makeLayer function. And then we run this for all of the 4 layers, and we set up what we need for the final layers that are similar for every resnet architecture. If you look here, right, in the original resnet stochastic depth linear decay call, you see we're giving stochastic depth basic block as the input, right? And this is this thing. So this is the block we're seeing in the stochastic, the resnet stochastic depth thing. We don't see stochastic depth basic block stated ever again. And this is useful because for 18 layer network, there's just the basic block. And for like past 52, I think, layers, this is where we have the bottleneck block, which we didn't see. It's the same thing, but like with the bottleneck architecture. And that's it. And then here's this layer things, this layer variable that we've seen over here, 0, 1, 2, 3. This is actually how much time we're going to repeat the given layer inside the given block inside the layer. So In our case, it was 22222 for ResNet 18. And if you look here, 2222 is how much time you're going to repeat the basic block in each of their specific layer. conv2, conv3, conv4, conv5 here. And if it was 34, it's going to be 3, 4, 6, 3, and blah blah. It will be different depending on the network size. Okay, so finally we're done with here with this make layer thing, the initialization. This is using the for function. And here there's the layers initialization that we're doing. Depending on which type of layer you're going to use, the initialization strategy you're going to use will have a big impact on your performance. So here they did 0 initialize last batch normalization, each residual branch, and then they get like 0.2 to 0.3% improvement. So this is actually very needed, and it's very empirically driven based on the latest literature. And that's all there is for the stochastic depth. Most of the stuff happens in the basic block. This is how we shut it off or on, and there's not that much different afterward with the ResNet architecture. Right, I hope this short tutorial was useful to understand stochastic depth. I highly recommend you dabble a bit with it, especially if you are training residual neural network and looking for a bit more performance and time saving. If you have any question, don't hesitate to leave a comment below, and I wish you all a great week.